Hi. So today we're going to talk about the idea of adversarial learning. Um, just a brief outline of what I'll be covering today. First, we start off with what motivated this, which is mainly the image generation problem. And then we'll discuss three papers. These are actually the three papers that Jeremy mentions in his lecture as well. First is the initial GAN paper by Goodfellow and everyone. And the second one is DC GAN. And the third is Wasserstein GAN. I don't know how to pronounce it. So yeah, that. After that, after looking at these three models for the generative adversarial networks, we'll take a look at how you can actually improve upon the training methods and what shortcomings these training methods try to address. Fourth, we'll take a look at a few applications, having understood what the model looked like, how we can train better, and then a few interesting applications. And then finally, I'll try to wrap up with this concept of adversarial examples, which is not exactly related to GANs themselves, but it's related to adversarial learning. So the image generation problem. So the image generation problem is basically, given a machine learning model, you should be able to generate an image about a certain topic, say, for example, objects in everyday life or a bedroom or whatever. But you don't want it to memorize pictures that you've already shown it. The main feature about the main problem with the image generation problem is that you don't really give it an input. You just expect it to keep generating images. So it's not like you're mapping from certain features to something else. You're just trying to create it from no input. So one of the better methods of doing this is through GANs. So this is the generic structure of what all GANs will be. There'll be a generator, a discriminator. So last week we learned that for style transfer you had for your loss you had two types of losses, which is the style loss and the content loss, and you use both of them to transfer style. Last week we learned that for super resolution you had perceptual loss, but in the case of generating images, it's kind of hard to define a loss as such because you're just creating images. You're not really trying to. You don't have a reference point to say whether this is really that good or not. So that was what the initial problem was. So the way they came up with a method of creating this loss function by having another neural network be designed to say whether this produced image is real or not. So that's the principal role of the discriminator, which is.
Sorry, the loss function, are you referring to the loss function for D or for Z?
Together, both of them together. So so basically the role of D is to identify, the discriminator is to identify the real image from the fake image. And the generator's role is to produce images and try to trick the discriminator into making it think it's real. So the discriminator will sample half the time from real samples and half the time from fake images or generated images. So looking at the cost function itself, in the initial paper, this is the cost function that they used. And you can sort of get an intuitive idea of why this works. So when you sample from the real samples, so you look at this, the first part of the loss. So you want to maximize the output of the discriminator. So the output of the discriminator is, if it's a real image, it'll output close to 1. And if it's a fake image, it'll output close to 0, as in lower values. So when it's a real image, you'd be ideally trying to maximize this and minimize this. You want to say that you want your discriminator to be able to say that the images from the real sample is high, so you want this to be higher and this to be lower. So that's why as a discriminator, you'd want to maximize this output. And for the generator, is the exact opposite. You're trying to minimize this output. I forgot to mention one important thing. So in all these GANs, they initially start off with a random vector, which is usually called a code vector or either a latent vector. So from this, it's exactly similar to what we've done in the past. We start off with some random noise and we just keep fiddling around with the pixel values, and then finally we get a new image. So the same way here, instead of starting out with a matrix itself, you start off with usually 100 sized vector for containing random samples sampled from a uniform distribution. So this is what the cost function would look like. So the general method for training a GAN is you decide on your architecture. Initially, the first ever paper, they used simple feed-forward networks. So it wasn't very complex and good at picking out features. It still performed pretty well, but it wasn't the best architecture out there. And in order to train, the main difficulty is that you need to train both your generator as well as your discriminator at the same time, because you haven't really told each one what to do. So the way they decided about going about this was initially freeze your generator, just pass the initial output of the generator to the discriminator, and then train the discriminator, pass the weights back to the generator, and freeze the discriminator. So you train it one by one. And the way they check the progress is, since you don't really have a metric at this point of measuring how well your training loss is or anything, they just look at the quality of the image generated. So theoretically, you can look at it in this way. So the black dotted graph represents the real distribution of the data. The green graph represents what your generated distribution looks like. So if you see at the bottom, there's a line saying Z, and above that there's X. So Z, like I mentioned, is the initial random code vector. So you're sampling from this sample space of uniformly distributed variables. You're mapping it to this space of images, which is your X. And the probability distribution of your real data is the black dotted line, and the generated data is your blue dotted line. Now, the job of the discriminator is to output a high value when it's pretty certain that it's a real data, and a low value when it's fake data. So as you can see that initially the discriminator is sort of unsure. It's that it's pretty confident that it's still in this area. You're more likely to get a real image, and once you go here, it's more or less certain that this is what the area where generated images are like. As you keep training, it gets better, the discrimination between the two, and the generator also learns to shift the data points towards the real data. Finally, ideally when you finish training, you would have a situation where the generated data overlaps the distribution of the real data, and the discriminator is completely confused, as in every time it doesn't know whether it's real or not. So it just keeps outputting 0.5, 0.5, 0.5. So the ideal situation is this. The one that you want to obtain after training. From the initial Goodfellow paper, these are a few of the results. You can see that, so what this means is the yellow boxes here, they are the closest images to the generated images on the left. So for example, if you take this figure here, the closest image in the training set is this 9 that they saw. So you can see it's pretty close, and it's learned to pick out features well for a feed-forward network, and this seemed to provide promising results. But for more complex images, it's kind of hard to see. Doesn't really look like a horse, but like, fine, we'll believe you. So the next step would then be to replace your feed-forward networks and try to get something a bit more complex and try to learn your features better. The second paper that Jeremy mentions is the DC GAN paper. Instead of using feed-forward networks, they use convolutional networks. This is pretty much the same thing as what we did for super resolution. Use a filter to create a large channeled input, basically. Keep upsampling until you get the final input. A few things to note in case anyone wants to re-implement this is that the discriminator uses leaky ReLUs instead of normal ReLUs. One of the reasons they say they do that is because it's easier to propagate the errors back with leaky ReLUs, because sometimes because it usually otherwise just cuts off the negative values directly. So leaky ReLUs, the form of the activation is that for the negative side, it's much less. It's a smaller slope, basically.
Have you guys all understood what a leaky ReLU is? No?
Yeah, that.
Okay.
Exactly.
So a ReLU is normally just a max of x and 0, right? So the problem there is you have a negative side that's all truncated to 0. So you have no gradient there. So what a leaky ReLU does is it sets the slope of the things past 0 slightly negative, right? So it's to encourage the negative samples to have some effect rather than truncating it off, right? Typically, when we are using a recognition scenario, we don't care about the negative part of the data. Just like when we do max pooling, we don't care about it, right? We just say, I just want to know whether there's a car there or not, right? I don't care whether there's cars anywhere else. I just want to know whether it's firing there. That's why we use max and ReLU, right? But in the negative case, when we're trying to discriminate and train an adversary, maybe the negative samples are more important.
Yeah.
Right? This is why we use leaky ReLU. Do you guys have any opinions or anything you'd like to share on that part? You guys are awfully quiet today. Maybe you guys are all doing your project. Okay. And why a tan H? Why hyperbolic tangent?
They don't really mention it. They just, for the generator, they just said it's to restrict the values between -1 and 1, but I mean, that's what a tan H does. So they didn't really mention why they do it.
Okay, they're just preferring the output to be between -1 and 1.
Yeah.
Anyone want to say why, or you guys want to look it up and then give us an answer? You're here ostensibly not just to listen, right? Also to participate. Yeah, sir. You're new in the class, right? Yeah. So you came in just this week. Your name again?
Lam Seng.
Lam Seng,
Yes.
Okay.
My guess is because your discriminator has a negative portion, so you need a tan H to match the negative portion. Because tan H is centered around 0.
Right. Compared to sigmoid, right? Sigmoid, you get 0.5 as the center, 0 and 1. So if we want to keep everything in the range of -1 and 1, then we'll need something that's centered at 0.
Yeah.
So you can use a leaky ReLU, but maybe you guys can think about what's the side effect of using something like that rather than something that's more like just an identity function of X, right? Because that's what we do for ReLU, right? We use the positive portion going to 1, but the negative portion is forced to 0. Now we're saying that negatives have a little bit of effect, but not a lot. So there's a tuning parameter that you can set with a leaky ReLU, right? Because you want to define the slope of the negative part. Okay.
Yeah, so this is the architecture for the generator. For the discriminator, they just use a normal, I think, 4-layered convolutional network for classifying whether it's a real image or a fake image. And a few of the results that they've gotten. Actually, yeah. So looking at, they used, they didn't use the ImageNet dataset initially. They'd use something called the LSUN dataset. They did this because for ImageNet, it has a large variety of categories, whereas compared to LSUN, which is just basically like bedrooms and
Furniture,
chairs
yeah.
and furniture.
It's
and
like
things.
the IKEA catalog.
Yeah,
of the
exactly.
deep learning model.
So, so they restricted to that to try to better learn these features. So, and having done that, they tried to prove that what it's actually doing is it's learned these features pretty well. So what they did was, I had said that they start off with a random vector of say 100 variables, which are sampled uniformly from a uniform distribution. So they started with, they took 10 of these random vectors and they tried interpolating values between these 10 vectors and generated images from these interpolations as well. So for example, if you start off with a random vector A and another vector B, they interpolated between these two vectors and they generated images using each of these interpolations. And they realized that as you move from the initial vector to the final vector, the images gradually change towards this final image. So they continue this and they do it for 10 separate examples. And there are a few interesting cases, like for example, in this one, I don't know if you can see it. So initially it starts off as a TV here, and it ends up as slowly becomes a window, and it uniformly transforms into this final image. So the main argument that the authors make is that since the network is able to smoothly transition from one image to the other, they argue that this demonstrates that it hasn't really memorized anything, because if it has memorized something, there'd be a more distinct transition between two vectors, initial vectors. Another interesting thing, a test that they ran on their these vectors is that just like how in NLP you have the usual example of king minus man plus woman equals queen, the same thing they did with their vectors for each of the faces. So they took the initial random vectors, say for example, for 3 images which had glasses in it. Now each of these 3 images were generated by an initial random vector. So they took the random vector for this, the random vector for this, and the random vector for this, averaged it and generated an image and got this. Similarly, they did the same thing for a man without a glass and a woman without glasses. When they performed this arithmetic on it, they were able to generate this central image. And the other ones here are just, they've just added noise to make sure that it's stable. And you can see that it is relatively stable, although not pretty.
The woman looks
Yeah.
not so much like a woman with glasses, but a woman who got eaten up badly.
Yeah, so this is another interesting test that they ran on their results. Another thing, this is very similar to the initial one of uniformly transforming between 2 vectors. They showed that rotations also map linearly within this space. So they start off with a left vector and a right vector. So they take a bunch of images with the face on the left and a bunch of images on the face on the right, and they try to interpolate between the two, and they see that the images actually seem to turn their head as you go from one end to the other. So that's what DC GAN was. And we also know, we looked at what GANs were. Now, the main drawback with the initial 2 papers was that the loss function that they used was not very well behaved, as in there would be points where the gradient suddenly becomes either 0 or 1, like binary, or the values jump to infinities. So what the authors of this paper did was they looked at trying to identify a different type of loss function that they could use to train their GANs. So if I go back to this, the theoretical backing for the GAN paper is this concept called Jensen-Shannon divergence, which basically is the way these divergences and distance measures work is you have these two distributions, and what you're trying to do is to test how much they overlap exactly. You have these measures called such as like Jensen-Shannon divergence or KL distance measures, things like that, which measure how well they overlap with each other, for example. So the GANs papers that we've seen so far are based on something called the Jensen-Shannon divergence. Now, this isn't a good metric to use at all the times, because this is one of the reasons which causes these not well-behaved functions. So what they identified was, instead of using this divergence, they would try to move towards this Earth mover distance or Wasserstein 1 measure.
Wasserstein.
Okay, sorry, Wasserstein measure. Okay, and
it's a German word.
Okay, Wasserstein. So you can sort of intuitively understand this Earth mover distance metric by, it's basically looking at two curves. You're trying to identify how much mass you have to move from one curve to get the other curve. So that's basically the intuition behind that, and that's the metric that they use. Now, to calculate this empirically, it's kind of hard because in the paper they make a bunch of assumptions and bunch of assumptions to ensure that the function becomes tractable, as in it becomes well behaved, and that you can calculate it at all points. But one of the assumptions that they make is that the weights of the discriminator have to be clipped within these two, within this limit. So, and the results of again, the same Elson database are shown here, and you can see actually that it's performs much better. And not only that, it avoids something called as the mode collapse. I'll come to this in a little bit, but this is one of the major problems that GANs face, which is mode collapse. Another thing that Jeremy mentions in the lecture itself is that initially when you're training these GANs, according to, say, the Goodfellow method, is that the losses don't really mean anything, because you don't really know if your generator has learned to really generate something well, or whether it's just learned to trick the discriminator for that very small subspace of the whole sample space that you want to generate. And vice versa for the discriminator, if it's learned to just discriminate for one specific thing. So here in this case, however, the loss function that they've defined allows you to actually see that with a lower loss function, it means that the quality of the image generated is better. So you have this intuition between lower loss and a better image.
So you guys all know about the difference between Jensen-Shannon divergence, KL divergence, and Earth mover's distance? You guys want to talk about it a bit?
My understanding about the KL distance The cross entropy is sort of KL distance, right?
Yeah, it's based on KL. So what is KL divergence? Anyone know? These are all different similarity measures for looking at distributions, right? So you have two different distributions. You want to calculate how similar they are to each other, right? So the more similar the distributions look, the closer the value is to 1. The more dissimilar, the closer it is to 0, right? These are all the types of measures that you have. So KL and Jensen-Shannon divergence are both measures of that. KL divergence is a little bit interesting because it's asymmetric. You may have seen that before. You're welcome to take a look at the links on Wikipedia, and somebody can put it on Slack. Why it's asymmetric. A lot of people who don't know better will take the KL divergence, and because it's asymmetric, they'll just apply an average of the two KL divergence in both directions. But usually that's not necessarily the best application for that. It's asymmetric for a reason. Okay. Secondly, you have Jensen-Shannon divergence, another way of incorporating that. So I'd like you guys to go figure out maybe interactively right now, because it's better used than just having our Venu lecture, right? So he's got another half slides to cover, but I think it would be worthwhile to get this down, because there are lots of applications in which you want to calculate a score of this. Okay. So one of the things about this is, when you have two distributions and you need to make one distribution similar to another, you can decide what type of similarity measure you want. Earth mover's distance makes a certain assumption that parts of the distribution close by to each other have some locality constraints, right? So when you explain that Earth mover's distance is a little bit like, if you look at a landscape and you imagine a bulldozer sitting on that landscape and trying to plow it into another distribution, the amount of work that the bulldozer has to do to level out some peaks and build up another peaks, right? So there's a locality constraint. You can't just take this heap of sand in one area and then transfer it to the other area with no work, right? It takes physical work to move it over there. Whereas, let's say, KL divergence doesn't measure that. It just says, whether the peak is close by or far away, it's the same amount of work, right? So there's some locality constraints within the distribution when you're talking about Earth's mover's distance. And why is that important to GANs? Why would that be important to do something like that? Because obviously they had a more intuitive choice, thanks Rajan, of just putting on, just using something like KL divergence or Jensen-Shannon divergence, because that's sort of the obvious choice, right? When you're using cross entropy, well, the natural notion is to stay with cross entropy, stay with KL divergence. So why they obviously had to have a reason to move to Earth mover's distance for it. Okay, so take a couple minutes, do your Stack Overflow, Quora, whatever examination, find out why. Okay, so maybe we can do this exercise for a couple minutes so that we can get a better understanding, and then if you actually do something with your investigation while listening to Venu, you will get more out of it. Okay, lecture without reinforcement is not useful. Just in one ear, out the other ear, right? So go find out. Okay, so if you have links, put them on. All right, John's put some on. Thanks for that. I'll put on another one. So if you're on Slack, you can go take a look at those things. It's actually sort of important, right? Because otherwise you're going to come up with another deep learning network and you won't know what loss function or what similarity function to use, and then you're going to end up with failed experiments. You're like, how come it doesn't work? I guess it doesn't work, right? So you have to be principled and understand the components involved. So I think you see from the Wikipedia page that Rajan put up, right? Oh, there's one more for Jensen-Shannon division. Right, so Jensen-Shannon divergence, as it says there, it is symmetric, and it's always a finite value, a little bit different from the KL divergence, which have a bound. If you want to bound a KL distance or divergence, you should probably push it into a sigmoid so you get something finite. So we try to get on this. Let's report back in about 2 minutes what you were going to get out of your cursory exploration. Anyone figure it out yet? Minor locality constraint is important for something like GAN or picture.
So I think, I mean, when you look at an image itself, isn't it that the pixels which are closer to a specific pixel have more similarity than, have higher chances of being similar than pixels further away? So you'd want a sort of locality measure to reflect that, right?
That's exactly right. You think of the picture as a terrain, right? Or maybe you have 3 terrains because you have RGB, right? And if you're moving the values of pixels from just one place to a neighboring pixel, that doesn't take a lot of work. But if you have to shove that pixel value all the way to somewhere far away, then it takes more, right? Jensen-Shannon divergence and any KL type based metric, right? Probably you figured out through some Googling or pages that Rajan put up that Jensen-Shannon divergence and KL divergence are very similar on this, basically the average of the other. You don't take into this locality constraint at all, right? So you know, you could get different images that are actually very similar in distribution, but look totally different because their pixels are in scattered, right? So the Earth-moving system is enforcing that locality constraint. Okay. Question?
The argument I did, but they talk about convergence. So I just quickly want butterfly down.
Okay, right.
They talk about that under this Earth-moving system, you have convergence which you don't have under the other materials.
Okay.
So that kind of gives you some benefit. Like, of course, then you can look at the convergence and you see something, while under the other two systems, the actual, like they don't need to converge, and then you don't see anything. But why that is the case? The stated material is included in
Okay, yeah, we're not going to go that deep into the picture right now. Okay, so it could be it doesn't converge because basically Jensen-Shannon divergence or FPL divergence doesn't give us fine-grained indication of whether things are similar or not. Because, you know, again, with the same divergence score, you could get completely different pictures, right? Because the distributions are actually the same. It's just the locality constraints are different. You can go ahead.
Okay. So we looked at three methods for the architectures for different GANs and different loss functions. Two sort of predominant issues that plague GANs is the first one is something called mode collapse. It can be understood by taking, say, for example, the MNS-IT data set. So if you want to generate handwritten digits, and you want your generator to generate images which can try to trick the discriminator into thinking, oh, this is a real image. Now, the generator can get really good at making one specific digit. So, for example, it can learn how to make 3, and it can get really good at it. And the discriminator might not be able to identify the difference between a fake 3 and a real 3. So it will constantly, it will learn to constantly say that if it's presented with the image 3, it will mark it as false, because that way it reduces its loss. So so the generator then learns to become really good at handling a very small subset of the whole sample space, and the discriminator just keeps marking that as false, false, false. And what the generator then learns is to switch to another digit. So it will learn to start creating 4s, say, for example, and it will get really good at that until the discriminator starts labeling all 4s as false. And so you have this weird situation where the generator just keeps moving to the next one and the next one, and the discriminator just keeps labeling it until the discriminator starts labeling all of them false. So this is essentially what mode collapse refers to. The other problem is the problem of overconfident discriminators. So initially, when you're starting to train the discriminator, you're basically getting noise as the input image from the fake, the generator. So it becomes really overconfident at saying, oh, I know what this is clearly fake, and then this is not. So then it becomes overconfident, and it sort of affects the results in the long run. After they released their initial GAN paper, Goodfellow and a few other authors, they improved the training methods for GANs itself. The architecture that they used is very similar to DC GAN, but they added a bunch of new features for training. Of these 5, ideally these 2 are the first 2 are the most important, as the results from their papers show, as they're able to achieve better results using that. The other three are good, but they don't really discuss the results of it that much. They use it and they say in theory it should increase performance, but the main results are the first two. So the first one is feature matching. So usually the generator is trained to deceive the discriminator. So what they decided to do, instead of trying to create the image, trying to create an image to trick the discriminator, what they try to do is instead try to get features for your generated image very close to the real image. So for example, what they did was the generator would create an image and you would take a sample image. And so you would pass the sample image through the discriminator and extract features from a specific layer. So and you'd store it somewhere. And similarly, you pass the image which you generated through this discriminator and extract features from the same layer. And you try to calculate the Euclidean distance between the two. And this would then be the loss that you're trying to optimize for.
Instead of looking at the output, it's just looking at the
Exactly. Yeah. So this is like trying to sort of generalize it and saying you don't really have to try to trick it for this specific thing. Just make sure that you learn to match the features. Yeah. Another way of this is a problem trying to identify. So, yes.
But so that kind of things with the architecture of BNP, which is similar. Otherwise, you can't. So you kind of need like layers to get match.
No, you're taking the layers from the discriminator itself. Okay. So
So okay.
Right?
Yeah, I see.
We're not using one method.
Yeah.
Yeah.
Of course, you use it.
And this is just for calculating the loss.
Yeah. The second technique is mini-batch discrimination. So one of the key characteristics of mode collapse is, given a mini-batch of examples, it'll all the images generated by the generator will be pretty similar. I think they look almost the same. There'll be a few variations here and there, but they'll tend to match the same. So for example, if it's learned to create only the digit 3, most of your images will look like 3. So what mini-batch discrimination tries to do is it tries to identify the differences in the images which are generated by the generator. So what they do is they take the features from the generated image, uh, which are extracted from a layer from the discriminator, and they multiply it with a tensor to get a bunch of matrices. So once you get these matrices, they calculate the distance between the two, specifically the L1 distance, and sum over that to get the like basically an idea of how varied the images are. So the more varied your images are, the higher chance of it not being a mode collapsation.
One other one. It's such much relation to the one.
I think it's just computational. I'm not sure. I guess because you'll be doing it a lot of times, right? So I think they don't really explain why, but I think it's for computational reasons. So these two initially are the most important results from the paper, I would say. The other few techniques that they use are something called historical averaging and one-sided label smoothing. Historical averaging is basically trying to penalize the network for trying to assign weights which are further away from the averages of what it used to be. And one-sided label smoothing is instead of saying having hard values says as 0 and 1, saying this is definitely real and this is definitely false, you try to smooth it out and say it's 0.9, like 0.9 instead of 1 and try to say that it's not entirely sure, but it's like smoothed out. They do, it's one-sided because they only do this for the higher side. They don't do this for the lower side because you wanted to be able to be certain that it's fake, but sorry, it's not certain that it's fake. They just use it for the only one side, I think, because for mainly empirical reasons, I guess. Yeah, but they suggested only using it for one side. And the last technique that they use is something called virtual batch normalization. It's similar to normalization, but instead of normalizing across a batch, they normalize across a reference batch. So initially they have a batch, they calculate their averages with respect to that batch and try to normalize using that. This is computationally expensive because you have to pass both the reference batch and the current batch that you're training for. And yeah, but yeah.
Can you go to the few slides? So yeah, what do you so what do you do to keep? I cannot understand what you're doing. So you change your batches if you are going to too small. So far it's just like a method to tell you
that it's diverse. Yeah. What do you do with that information?
Yeah,
I think it's so one is that it lets you identify whether your model is performing well. So so you know whether it's in a more collapsed state, right? I think in the other method is that if it is not being very diverse, I'm not really sure about this actually, but I think you would have to penalize your generator in some way because you're not creating diverse enough images, right? So I guess that would be what I would say.
it's more like it's primarily a detection and the field detect and flow a lot of learning
out of it. Yeah, I think that makes sense.
But I mean, a couple of these tricks are all about GANs or getting too confident about it. Not generalizing this.
Yeah, this again is another result which sort of seems surprising initially is that to generate images, they also tagged along with it this task of semi-supervised learning. So what they did was, along with generating these images, they also tried to classify unlabeled data along with it. So for example, they would have basically the discriminator would have the task of not only identifying whether the image is real or fake, but at the same time it would have to label the data if uh, given a training data set which has the corresponding labels. That makes sense. So what semi-supervised learning is basically is that you have a small set of labeled data and you have a large set of unlabeled data, which is usually the case in the wild. And what you want to do is to be able to have your model learn to label the data using as much little training data which you have, which has the labels. So again, just quickly brushing over this is that the model would then be, you'd have, instead of two classes as being real and fake, you would have, say, for example, if you had k classes or k labels, you would have a total of k plus 1 labels that you would have to predict. K initial labels for the classes of the images themselves, and 1 extra for the fake image. So if it's pretty certain that it's a fake, you just say it's fake. If you think it's real, then you identify the labels as well. So the loss function that they use is a combination of a supervised and an unsupervised loss. The supervised loss is can be seen as trying to generate the correct label given you have the data and the label. For the unsupervised loss, it's saying that you need to output that it's a fake given that your image is from the generator, and at the same time penalize it if it outputs that it's fake if it's an image from the real data set. So that's roughly, like, intuitively what this loss function is trying to say. A few important results and like takeaways from this paper was that when they used feature matching and semi-supervised learning, they perform better at semi-supervised classification tasks. The second one is that when you have mini-batch discrimination along with semi-supervised learning, the images actually tend to look much better. And overall, they say that using semi-supervised learning generally makes the images which were generated to look much more visually appealing. So do you guys have any idea of why do you think that is? As in, it seems kind of counterintuitive to say that the way to create better images is to also start classifying a bunch of other ones.
You guys have any input on that?
So the reason that turns out to be true, I mean, they hypothesize it is true is because they say that having access to these labels of for labeled data also provides information that the model can learn from. So it sort of transfers into this the generation aspect of it. So that's what they basically hypothesize. So it's able to identify that. So if you say like this is a car, but this is also a car, and you have sort of very different images of it, they realize that, oh, okay, these are somewhat related, and I can generate it, use certain features to from both of these to generate it. That makes sense.
Kind of, if you start and the generator kind of generates parts with rings. Don't make sense if you don't, like, because it's a mixture of possibilities. Exactly. If you basically say, okay, I can have cars or planes, but the mixture in between is not there.
Yeah.
Then being able to differentiate between particles might help you.
Yeah, that's
identifying.
Yeah, that's pretty much.
And also, like, it's just which data sets do they use? Because you said in the wired, usually you have a small data set and then large unmeasured.
Yeah.
So it could also mean that you just have a lot more data to train if you.
No, I think.
They use CIFAR.
Yeah. So they use CIFAR and for whatever the pronunciation. They use all the usual data sets. They use this. They use ImageNet, and they also use MNSIT also, I think. So the unlabeled data, I just think they don't pass the labels along with it. They just use the. So we've seen a few examples of GANs and images. GANs and text also have the main difficulty with GANs and text is the fact that pixel values are continuous, whereas your bag of words is not, basically. You have discrete values, and you can't really, when you try to backpropagate that, since the discreteness is a big factor. There have been a few approaches to incorporating GANs into natural language processing. Most of them, a few of them use reinforcement learning also to create this ideal sample latent vector. But again, I didn't go into that deep.
Okay, can we go?
Yeah, try to wrap it up.
Let's go back to the semi. So do you guys know why the semi-supervised is better? This really comes from. We go back to the intuition part of it. It's like Venu was saying, right? When you have the problem of doing a GAN, you just decide the discriminator is just deciding real versus fake, right? You have this problem that is just a binary. And when you make it into the semi-supervised problem, you also have to decide, what type of image is it, right? When you're doing a classification problem, you need to give confidence, right? And then exposing it to more images allows it to, it becomes a joint problem, not just distinguishing fake from real, but also trying to distinguish what type of thing, right? So when you have a joint problem, you have two problems collected together. Sometimes that's more powerful because you get more information better than just having. So having the semi-supervision is pulling out, as Martin said, some real examples from the training data, right? Or untrained data, right? Because obviously the unlabeled data is still real, right? They're real objects, and so they have some bias, right? Cars like cars. So because of that change from using just binary output to something more continuous, you're that very complicated. Right? So this is another case where something like a joint learning problem turns out to be more effective in trying to make the problem harder, but you provide it with a different type of input, where the input is unlabeled but displaying some higher probability, right? Because real objects in unlabeled data will cluster in certain ways. That's to make better representation of or images, not personal images.
So a few applications of GANs which are kind of interesting. Text-to-image synthesis. So given a description of a bird, the generator is able to generate this. So the way this works is basically initially, instead of just starting off with the random vector, you also concatenate the embedded vector for your sentence, basically. And when your discriminator is identifying whether it's real or fake, it also has access to the same word vector. So this is basically the key takeaway, as long as you don't really have, as long as you concatenate it and give access to it for the discriminator as well, you can actually generate images from text using a description.
You see that in almost all the networks. Animation, right? You may have seen the video captioning type of work before. You can do this with audio, right? You can generate from you some random things or give a good description of what I don't know, sounds like.
Yeah. The second one is something called progressive growing of GANs. So if anyone actually went for the NVIDIA talk, the speaker spoke about precisely this. This is the work done at NVIDIA. And so the basic idea behind this is that instead of trying to generate this huge image initially itself, this 1024 into 1024 image, they start off small. They say, okay, fine, generate a 4x4 image. Then they move progressively higher, 8x8, 16x16, so on and so forth, and until they get to this. So this is important because it drastically reduces the training time, as well as creating much clearer images. And you can actually get a sense of it if you just watch that. Yeah. I'll just skip through it really quickly. So all these are yeah. So you can see they start off with the 32 by 32, 64, and as they progressively learn make the network bigger, the images start becoming more human. So you can also see the training time as it goes on. And the other main thing is similar to how in the DC GAN paper you had these interpolation between these initial vectors. They did the same thing. So it's kind of creepy, but it's basically the same idea. As an interpolation between the two initial random vectors gives you various images. And yeah, this is basically the main crux of what they did. The last thing I'd like to talk about is something called adversarial examples. Adversarial examples are examples which seems to break the machine learning model that you have. So for example, if you have this initial image of a panda and it's 57% confident that it's a panda. Now, if you add some noise to it and you're not modifying it but by that much, you're able to trick your machine learning model into saying that creating an altogether entirely different label. So one of the methods of generating this noise is to get the sign of the gradient at each point. The other method is to use the gradient in the direction of the closest label. So that is what they use in this one. So for example, the funny thing about this is the common thread between all these images is that all the images on the right were classified as ostriches. So initially they started off with a school bus. They provided the noise and they get this image, which looks still like a school bus, exactly. But, and I'd like to point out that it's labeled an ostrich with relatively high confidence. So for example, here it's 99.8% sure that it's an ostrich. Now it's understandable that fine, it might be just a one-off case, but the fact is you can actually do this for a bunch of examples given the right amount of noise. Another important aspect of this is that you don't actually need to modify the initial image. So for example, if you take a printout of a cat and you, if you take the image of a cat and you add some noise to it and you take a printout of that image and you then take a picture of that printout, it still contains this weird bias in classification. So for example, even if you have the object be partially occluded or like tilted at a different angle, whatever, this, you probably can't see it, but this is labeling it as a desktop computer. Yeah. With high levels of confidence.
But the point was, we also discussed that same thing in the previous classes. So that in the image, in the case of image, the one thing that highlights is the pixel with the higher color intensity. That really matters. Like if your eye, you're just concentrating on that black portion. Okay. Yeah. If you are adding a noise over that, that eye will remain the eye. It will not going to change because noise is not going to affect the colors with the high intensity at all. They're going to affect the color with the low intensity. So that could be a reason that it shows this kind of results, because the point is that even if you add the noise, you're like, we can take the example of class. If your class is the building students, that's like pixels with the high intensity, they are not going to suffer with the noise. They are going to remain the same because they already have a very good intensity of color. So Noise is not going to affect them. So the picture will remain the same even if you add the noise. Even if you add the noise so much, then you differentiate by the other, it will remain the same. So I don't know how they are just both images are same. The car is the car. There is no change in that.
Yeah, visually it doesn't look that different, but
specifically adversarially taking the gradient of the image, adding it into the example. So it may not change the picture a lot to your eye, but because of the way the next page is working, only certain pieces of information that is affecting the figure's distance. That's fine. So I think these are problems that are eventually going to be solved.
Example. I mean, there are even examples where you take a picture, like you take like a stop sign, put on the sticker, take a picture of that, and the machine learning algorithm thinks it's a different time. So you don't even need to do something sophisticated. It's pretty easy. You can just put a sticker on and stuff.
Exactly.
And you press down. That's of course taken because it's an example that everybody can relate to. If you have an automatic car and you have people running around putting stickers on signs, your cars don't break.
Yeah.
But yeah, so there was some work about like robustness because these pictures are relatively close to each other when you consider them L1 or L2 norm. So now people are trying like to get robust, saying okay, if your pictures are close to each other in the norm and all the norms you can think about, then they also should be the same. So we try to get a sense of how humans think they are close.
So, certain cards seeing stop signs as not stop signs. Another example would be identity theft. So, for example, if you put like a sticker on your face, you can essentially become another sort of person. So, I think somebody actually did that. They took a sticker for like glasses, and they were able to trick the network into thinking they were a female actress of some kind. So, yeah, that's about it.
Okay. Let's thank Dr. Zinko. So we have 2 more classes, one this week on Friday and another one next Friday. So I hope all of you have something back if you're part of the extension. Okay. Thank you.
Thank you. Thank you.